Thanks. Maybe, possibly you know what functional fields are and you don't know what existential first order definitions are, so let me start with this. So when I was a PhD student, my supervisor always said, never start your talk with a definition. This was more than 4 years ago. So let me just take an arbitrary field f for now. And take some natural number. And I want to define what it means for a subset of, let me say, f to the n to be existentially definable. Definable. And if I have to keep writing such long words, they get uglier and uglier. So let me write this for now on the board. Okay, so I will never say first order again, but it's here to suggest that this is a notion which comes from logic, first order logic, and it's also many of the questions I will talk about now are also motivated by questions from logic, which I will mostly ignore for the context of this talk. If you know what it means, existentially first order definable, then you don't have to follow this definition. It's exactly what you think it is. If you don't know what this is, you can actually define this entirely without logic, which is how I will do it for this talk. So it's called existentially definable. If and only if I can find additional integers k and m. 0 is a natural number for me. And polynomials, f1 up to fk, over f in n plus m variables. Let me give them different names, x1 up to xn, y1 up to ym. Such that the set A can be described as follows: precisely those n tuples in F, which can be extended by an m tuple to a solution of the system. F1 up to fk is equal to 0. So if m is equal to 0 and this y is not there, this is just a Zariski closed set, right? This is a more general notion. It's, well, if you want, it's the image on their polynomial map of a Zariski closed set. It's a projection of a Zariski closed set. So this contains Zariski closed set, but it's more general. Okay. Examples. So I mean, you could ask, why is this a sensible notion? Let me avoid asking this question, answering this question for now, and just say, okay, what can these sets look like? And let me do this with different fields. So each time let f be a field, and let me fix n equal to 1. So I'm just looking at subsets of f itself. So for example, what if I take the field of complex numbers or any algebraically closed fields, and I ask, what are the subsets of f which are existentially definable? So it's easy enough to see that any finite subset, well, it's Zariski closed, will do, and any cofinite subsets, so a set whose complement is finite. Easy exercise. And in fact, and this is a deeper theorem, these are all the existentially definable sets of an algebraically closed field. So this is, I guess, due to Chevalier. I mean, he didn't phrase it like this. Let's just say old, before 1950. Let's take our next field, slightly more complicated, the real numbers. So, I mean, finite and cofinite sets, actually for any field, they are existentially definable. For real numbers, you can do a bit more. You can define any finite union of intervals. So an interval can be its connected subsets, so open, closed, half open, and so on. Singletons are also intervals. And again, to see that these are always existentially definable is an easy exercise. To see that nothing else can be is more complicated. So this is due to Tasky. Published around 1950, but circulating before this. And if you know what p-adic numbers, I didn't want to change color, just chalk. If you happen to know what p-adic numbers are, then also in this case, let me just say some classification exists without writing it out. It's more complicated than for R. One can classify in a way which humans can understand what these existentially definable sets look like. This is Axel and Kochen, around 1970, 1966. So the general vibe here, which I want to convey, is that as your fields get more complicated, what does complicated mean? I mean more obstructions to equations being solvable, more complicated to decide whether equations are solvable, the richer this family of existentially definable sets might be. Right. So we need, for example, if I would now ask this question for the rational numbers, classify all the existentially definable sets of the rational numbers, this is pretty tricky. It may be that, if you know what this is, any recursively enumerable subset, so anything, this is some notion from computation theory, essentially any set for which you could write an algorithm to produce it is existentially definable. We don't have a counterexample to this. I mean, in fact, to construct some set of over Q, which you can show not to be existentially definable, might be quite difficult, even though, of course, there are uncountably many subsets of Q and only countably many systems of equations, so there's only countably many existentially definable subsets. So most of them are not, but yet randomly you would probably write down one which is. So maybe lots of sets. The big question in this area, to give you an idea of big unresolved questions, I could look at the ring of integers as a subset, I mean just as a subset of Q, and ask whether this is existentially definable. Somehow answering this question would help us find an explanation over Q, and we have no idea. Okay. Now I want to point out that showing that a set is existentially definable, there is at least somewhat of a strategy how you should do it. I mean, you write down a set of equations, you show that it does the thing you want it to do, showing that it's not existentially definable. This is more difficult. So there are existentially definable subrings even. Subrings of Q. Sort of show this. So let P be prime, the prime number. And look at the following ring. Yeah, what is this? So I mean, sort of all those rational numbers where the denominator is not divisible by P. So this is a local subring of Q. It's a valuation ring, if you know what this is. So it's a maximal proper subring of Q. It's a really big subring. And essentially, although she doesn't say it like this, but all the techniques are there, Robinson shows in 95 that for any P, this set is existentially defined. Let me give you a way to do this for about half of the prime numbers. So proposition, let P be prime and congruent to 3 mod 4. Then, let me now really make a claim which doesn't say anything about existentially definable, just some equality of sets. I claim that ZP is precisely sort of those rational numbers for which the following equation is solvable. Yeah, now it's nonsense if I don't check. 1 plus P minus 1 times P times x squared is equal to y1 squared plus y2 squared plus P times y3 squared for some y1, y2, y3 in Q. Okay, so if I would want to prove this, this would of course be this is a number theoretic thing that you need to prove. So you have to show if I take some element in here, then I can solve this equation in terms of y1 and y2, y3. And if I take some rational number which doesn't lie in here, then I cannot solve this equation. Let me not even call it a sketch, proof keywords. I mean, to give you some idea, so what happens here in this description, which is not necessary for general existentially defined, is it too small?
This is P minus 1?
This is P minus 1, not P times 1. This would not be useful to write. 1 plus P minus 1 times P times x squared. It's like this. So what happens here in this specific set, which is, in general doesn't have to happen, is that all the parameters, so the x variables are on one side and the y variables are on the other side. So we're saying fix some x, and we're asking whether this element of Q is represented by this quadratic form. And if you know some number theory, then you know that this is whether something is represented by a quadratic form is an entirely local condition to check. You only have to check it all at all the primes and infinity, and then you just believe me or check at home that I chose all these parameters in such a way that this is exactly the local condition you get. Hassan-Minkowski's theorem. So only local conditions. And that's how these questions can be done. Or when I first gave a talk mentioning this in November, I had already checked before whether AI can prove these kind of things, and it totally can. So this is now completely within the realm of possibilities of frontier models to do it perfectly. So now let me go to the function field setting. So just appetizer.
You mean AI gave you a proof that was elementary, not using Hassan-Minkowski?
No, okay. And yeah. do it yourself, or thanks. No, and I mean I want to emphasize this a little bit. This I came up with myself. Like I said, Robinson didn't exactly prove this, but all the techniques, modular arithmetic, are there. So it's not like this that this was found in some book. It really is able to piece together these arguments. So just to be on the same page, I assume this is nothing new. And I start with the fields, then KT, so just joining some transcendental elements, I will call the rational function fields in one variable without practice, or say this. And if I would, fix K, and if I would take some finite extension of finite field extension, and I just call this a function field in one variable or a function field of a curve. But in this talk, all function fields are often seen as function field over K. And really, I might be interested in general function fields of general curves, but to make this talk slightly less technical, all my examples will be just about this case. So the function field of the affine line, or the projective line, if you want. Sorry, were there any questions about this exactly parts? Yeah.
Which AI did you use?
Yeah, Google Gemini. Most fun. I mean, it gives you the most right answers in my experience. It also gives you the most confident wrong answers. It's still good work.
Was there a geometric motivation that got to this question, that brought to this question, or was it just an interesting question to ask?
The existentially definable sets. I think of it more as an arithmetic motivation and a geometric motivation. Right? So over algebraically closed fields, this doesn't tell you anything. For me, this is more of a way to measure the complexity of a field, like a way to, I'm a field arithmetic if I have to self-identify, so I like to look at fields and think which are the easy fields, which are the hard fields, and having a lot of existentially definable sets is one of many ways to express complexity in fields, as I was trying to sketch in the example. But that's how I think of it, but I'm not a geometrist, so I'm not the right person to ask.
Since you are asking from a geometric perspective, I mean, these are projections of closed variety, so is this not the standard geometric object also to look at?
I mean,
the current body is of a fine variety, so you don't have a. Yeah, so you can have open or closed. Yeah, so that's it shows.
Overall, this is an algebraic set.
Yes, over R this coincides with semi-algebraic sets. Yeah.
And is there anything going into omnimality? They also have a definitely definable not in the. Yeah, I don't know.
I mean, yeah, of course. I mean, actually, this definable comes from logic, so you can define this from for any kind of structure which has first order logic structure on top of it. Yeah, I'm not exactly sure what I can give at this point to answer this question.
So this property is stable, I guess, under finite unions?
Yes, indeed, finite unions, finite intersections, not complements in general. And there's also alternative definitions which come down to the same. So maybe you could also add in some inequalities. I mean, not greater than, this is not having fields, but not equal to. And this would also give you the same concepts. Because the set of non-zero elements is the projection of the set of invertible elements. So like you can, if you allow an arbitrary number of extra variables, there's many variations which come down to the same.
So the conclusion for C is the same for any. You never use the fact that it's C, right? I mean, you're just looking at polynomials.
I mean, the second one you just need real closed fields. So okay, so we are now looking at function fields, and I can ask the following question. Yeah, what's the analogous question to the one over there? I could say, is the ring of polynomials in this field existentially defined? Now, of course, this might depend on the field K. We don't know of any positive answers. And we also know that the answer is definitely no in some cases. For example, if K is equal to C. So somehow this is a good analogy with the case of C, where the problem turns out to be very hard. And this example here might inspire you to think that maybe this is not the right question, or not the easiest question we can answer in this context. There are other subrings of KT which would look more like ZP, which may have more chance of being existentially definable. So, I guess in general, you would call them discrete valuation rings. You know what these are, but we go to specialize to more examples. Right, if you take such a field F, like here, then you can look at the following subring. Let me write it by infinity of those fractions of polynomials which don't have a polar infinity, if you like this language, or otherwise you say the degree of the numerator should be bounded by the degree of the denominator. This gives you a valuation ring, or discrete valuation ring, even. And you can ask whether this may be existentially definable. And this, at least in some cases, is known to be the case. And let me mention the first one of these. Due to Denef, 78, I think. That's KPR. Yeah, so I may not keep repeating this. So F is always this rational function field over K. And all infinity is always this ring. So infinity is existentially defined. And I want to give you a sketch of how one could prove this. I'm not going to give Denef's original proof, although many of these are the same. I'm saying this because the first time I showed this was in Leuven, when I thought I should mention Denef's result. He was a professor here for a long time, although I've never met him because he retired before I started. And I didn't emphasize this enough that I was not giving his proof, and at some point I hear someone in the front row I've never met whisper to a colleague, I don't remember doing it like this. But, so, okay. Maybe I'll just, Any questions? All right. So here there will be a bit more geometry, a little bit more geometry. As these function fields have and the geometric nature. Solve this later. So, proposition 1. Well, firstly, in this setting, this is not dry enough yet. I claim that I can look at this, the field of constants as a subfield of RT, and I claim that this is existentially definable in RT. And let me, in fact, I can write you exactly how it is. R is precisely those set of rational functions. Okay, I will mess this up again if I don't check. Let me call them Y. I'm switching the names of the variables now, for which there exists some rational function x, for which y squared is equal to x cubed minus 4. Can I explain this? Well, that's the easy direction. Surely if I take some rational number y, then I can set x equal to the cube root of y squared plus 4. I mean, y squared, I mean, everything has a cube root in R, so set x equal to the cube root of y squared plus 4. Easy. What about the other direction? Suppose x were some non-constant rational function, and you had that y squared is equal to x cubed minus 4. What this gives you is a rational parameterization of this elliptic curve. So this gives you a morphism, a non-constant morphism from P1, is this correct? Yes, from P1 to the elliptic curve, I mean, this elliptic curve. And we know that this cannot happen. This is genus 0, this is genus 1. So elliptic curves don't have rational parameterizations, that's the point. Good. Nothing deep about this. It's just 2 propositions, so I have to make sure to do this. If I take some arbitrary function, arbitrary rational function, then the following are equivalent. On the one hand, f is a sum of 2 squares of rational functions. So this is some existentially definable condition. And secondly, how can I detect this? For any x in the domain of f, I mean, it's a rational function, it's a function from R to R, right? I think of it as a function from R to R, except that it might have finitely many poles, so I exclude these. F of x is 1. X is non-negative. Yeah, one implication is easy. If you're a sum of squares, then you can only evaluate in sums of squares, and then you will have to be, you can only evaluate in positive elements. And the other direction is actually also an elementary exercise. So you show this by induction. You first show this for polynomials by induction on the degree, and then this works for arbitrary rational functions. And then we go to the final and the most innocent looking proposition. Which says the following: take some element which actually lies in this O infinity, so some rational function where the denominator has degree higher than the numerator. Assume, or what do I want to say? No, assume anything. Yes, no, I want to assume. Without real poles. So it gives you a properly defined function from R to R. Then I can find some number y in R such that if I shift f by this number in R, then this is greater than 0 everywhere. And this I can really prove using a picture. I mean, what does this thing mean? Because remember from high school, I mean, if you're a fraction, if you're a rational function where the denominator has higher value than the numerator, it means that you have a horizontal asymptote, right? Right, so this condition means that in the limits, this function f converges to some value. Like this, this is the limits. F of x goes to plus or minus infinity. And then we have a continuous function without poles, so it goes like this. So it may have zeros, right? So I mean, it doesn't satisfy this criterion, but kind of on any compact interval it contains a minimum, so we can just take y. So like this is minus y. And this works. Now I can show this theorem right away. So for u in f, I should say, we have that for u to lie in here is equivalent to the existence of some y in R and some g1, g2 in f, such that if I shift my function by y, I get positive. I get the sum of two squares by this proposition. 2. But I want to make, I mean, I start with some u which maybe has some real poles, and if I want to apply this proposition in V, then I don't want to have real poles. So I want to shift away from this by some well-chosen rational transformation. Let me just write it down. I'll clarify all the details. Plus t squared. Like this t squared plus u squared. Yeah, so the thing here to, if this claim holds, then clearly we are done, because this condition on the right-hand side is existentially definable. Because to say that something like in R is existentially definable, this is also just about solvability of equations. I mean, the real thing to check here is that what you kind of show that this thing never has real poles. Because somehow any pole which you might have occurs in the numerator with the same degree as in the denominator, so they cancel out. The denominator cannot introduce any new real poles. And if you then would compute the associated valuation to this, then you see that it also kind of preserves whether u has negative valuation. Let's see what it says. It's positive or non-negative if u has non-negative valuation, and otherwise it's minus 3. So this you easily compute, and then it follows, right? So on the one hand, if u was lying here, then after this transformation you have no real poles, and you still lie in this valuation link, so this proposition 3 tells you you are done, together with 2. And in the other direction, if u is not lying here, then this thing has a pole of order 3, and a rational function which has a pole of order 3 goes to minus infinity on one side and to plus infinity on the other side, but then there's no amount of shifting you can do by a factor y to make this positive. Okay, there's a reason why this is proof. If you're wondering why this is proof. Any questions about this while we're like okay.
This was fast. Can you say this once again?
Sorry, the final part here?
The whole part. So you say, yeah, I mean, how this builds up with the 2 propositions.
Okay, yeah, sure, I can do this. So I have to show 2 implications here, right? I mean, I'm saying if this claim is proven and the theorem follows right away, so I just have to show the equivalence of these 2 statements. So let's go first from left to right. If u lies in O infinity, in this valuation ring, then I claim after transformation, I get something which still lies in O infinity but has no real poles. It lies in the real holomorphy ring, if you know what this means. And then this proposition 2 says I can shift this whole function upwards to get something which is everywhere non-negative. So that's proposition 3. Proposition 2 says if you're everywhere non-negative, then you're a sum of two squares.
So this was one implication, or both?
Yes, this was one implication. And then the other implication, sorry, let me dry this so it has some time to dry while I talk. For the other implication, I'm saying, suppose you don't lie in here. Then if I leave this computation down here, it means that this function here has a pole of order 3. Now, if you remember from high school, if you have a pole of order 3, so this is saying the degree of the numerator is 3 higher than the degree of the denominator, then your rational function, if you draw it, goes to minus infinity on one side and plus infinity on the other side. I mean, it might be flipped, but it goes to minus infinity on one side and plus infinity on the other side. But then there's no amount of shifting I can do by some number y, upwards or downwards, which is going to make the function everywhere positive.
Can I
Yes.
Between the interruption, like the property you are using of O infinity is okay, the reals, and then you can do this thing of being a square and being positive is kind of the same. And the fact that you can, my question, so okay, the first question is why the same proof doesn't give you that the set localized by one element and by t is also E definable.
Oh, I mean, it totally is. I mean, right? So, I mean, even a posteriori, you can have an automorphism of kt, which maps this valuation ring to any other valuation, any other real valuation ring. And then, so if you apply the automorphism to all the coefficients in this definition, then it gives you an existentially definable existential definition of any other real valuation ring.
I'm out of the valuation model. I localize by a single element. Like I take, fractions of polynomials where the denominator is a power of a fixed thing, right? I mean, this is a special collection of subsets of your thing, right? Which is you localize by the complement of, of polynomials, say, vanishing or having four.
Yeah.
But fractions of polynomials where I can declare, okay, what lives in the denominator.
Yeah, I mean, to some extent this works as long as you're only working with real poles. The problem is that this field R also has these functions like, I don't know, x squared plus 1 over x squared plus 2. I mean, as far as real poles and real zeros are concerned, this is everywhere invertible. But I mean, somehow this technique doesn't allow you to say anything about complex zeros. This is my issue. So how would you, if you want to just define, say, how is it, RT T inverse? Sorry, I'm using x instead of t, but you got it. How would you avoid things like this lying in there? Right? Somehow, this argument here completely ignored complex places. That's what I'm saying. Or maybe you can do it, and I can't, but.
I'm still not getting it. Is it possible to just write a bit more down on some intermediate thing?
Sorry, let me check a bit if I'm willing to sacrifice enough other parts. I guess I am. So, but you should tell me which implication. Why should I say more?
The steps, like okay, so you say something about this function that you didn't get a name, which is on the left side of the equality, and that this has the property of having never real poles. Then there comes some computation. Is this now? What's the role of it?
Well, it's t times something to the square.
Is this the explanation why it never has real poles?
No,
or should I just already see it?
To show this never has real poles, to show this thing.
Okay.
Okay, so should I explain why it never has real
maybe
poles?
explain to me why the two things together give this.
So which direction would you like?
okay, these two things together give both directions.
Yes. And
Okay,
the other propositions
then I
up there.
believe this. Then I can pass the structure of the.
Now the board is right. Wonderful. Okay, so one thing which maybe you already hinted a bit at is what's the role of the real numbers here, and this is precisely the question I kind of want to ask. So, what is known about existentially defining valuation rings? Maybe let me say specifically O infinity in KT for general K. So, right, so this case of, when it refers to characteristic 0 maybe, so this case of K equal to R. Or Q also works. This was done by Denef. 78. People found arguments for QP in certain subfields. Let me not be too precise about this. Okay, a long list of people, let me permit myself to just say them. So Kim and Roche in the 90s first worked on this a bit. They didn't exactly say something about defining valuations, but the techniques were there. And this was made precise in work of Eisenträger, Morebailly, in the PhD thesis of Claudia de Jolte here in Ghent, in later work by Russell and by Russell Miller and Sascha Schlappentoch. So yeah, so these are arithmetic fields, not C. I'm not putting that on purpose. Yeah, so there's certain subfields, including number fields. This also generalizes a bit this case. And a positive characteristic then this is known to be possible if K does not contain algebraically closed subfields. Yeah, and all these techniques, I mean, I don't have enough time, and you might not care enough for me to illustrate exactly where all these techniques are similar and where they differ. This was developed starting by the work of Rulli in the 80s, and then Fedaz and Videla in the 90s really made this precise. And then there was a series for finite fields K, and then there was a series of papers by Kim and Roche, by Eisenträger and Schlappentoch to eventually get this down to this precise condition, not containing algebraically closed. Okay, I had many, so this I worked on during my PhD thesis. There's many questions you might ask and questions which I had. I mean, one question which I cannot keep avoiding forever is why? I mean, the specific reason why so many people looked at this, and also I sometimes say, well, people didn't exactly say the valuation rings, but they still kind of did this. It's many of these things are come from decidability questions. So questions of the form, can I find some algorithm, which in this case tells me whether a given system of polynomial equations had a solution over a function, which you can also translate into a geometric question. Can I find an algorithm which tells me whether there exists a map from this curve to this curve or something? Whether for a general curve there exists a map to this curve. And these are in ways which I don't explain, which I've not explained, linked to this question of finding enough, showing that there are many existentially definable subsets of function fields. But the other question which comes from the proof I gave and from all these special cases is what's the general framework? I mean, is the answer to this just yes in general for any field? And then why are there so many different proofs for so many different base fields K? So let me give you the results. Complex theorem A, let me call it theorem B. So this is to a large extent done in my PhD thesis together with Karim Becher this year, and with Dittmann, my other PhD supervisor. Preprints in 2023, but it's still under review. And then slightly expanded by myself last year. I'll comment on the attribution soon. And it says, okay, let K be any large fields. I will define large. Keep it just in your head for now. Which is not algebraically closed. So this is to be defined, this is focus, not algebraically closed. Then, for infinity, it's existentially definable in K. In fact, that means in the interest of time, not write more, but just say more. Really, you want to be able, really, under essentially these conditions, you can existentially define any discrete valuation coming from a point on a curve in any function field on the curve over such fields. Except complex points over function fields over R, as I was saying earlier. Okay, so I said this, but I'm not writing this. So I should say what these large fields are. This is a notion which was introduced in the 90s, goes by some different names as well, like ample. The field is called large if every smooth curve over K has either no or infinitely many K points. Or another way of saying it, if every curve over K has either no or infinitely many smooth K points, it's the same. Comes down to the same. So what are examples of large fields? And also where does this come from? So large are, for example, the real numbers, the complex numbers, the p-adic numbers. In fact, any complete topological fields. So this covers the previous examples, but also certain fields which have no topological origin at all, like, for example, any algebraic extension of a finite field. Very non-topological. Let's do a quick sanity check. Why do the real numbers, for example, satisfy property large? Well, if you have a smooth curve over the real numbers, and you have some rational point, and the implicit functions theorem says that you have kind of a neighborhood around this point where you can locally invert the function. So you get, in this neighborhood, you get infinitely many points. You get uncountably many points, even. So in all these topological cases, it's the implicit function theorem which gives you this large. And the way I think about large, and it's really not a bad way to think about large, is what are you left with as an algebraic shadow of when you have the implicit function theorem? If you take the implicit function theorem, but you're not allowed to do analysis, what algebra is left, then you could say it's this property. Maybe I should give some non-examples. Of large fields, non-examples and non-large fields. Number fields. And function fields. Right, so over Q, you definitely have elliptic curves with finitely many points, for example. Okay. So this theorem, it provides a common framework for some of these examples, but not for all of them, right? Not for the number fields, for example. And not for finite fields. But yeah, it's a step.
Sorry, can I be confused by the example of the algebraic extension of a finite field?
Yes.
So if I take a finite field,
Thank you. Any infinite algebraic extension. A finite field is definitely not large. I mean, that would be a terrible name. Thank you. Yes. So, yeah. So, maybe before I continue, what are some notorious open cases? So maybe of course, this theorem also covers some new cases. So, for example, a new case would be any large fields containing some algebraically closed subfields. So maybe you could take the field of formal Laurent series over C or something, this would be a large field. It's a complete topological field, which is not covered by any of the previous techniques. But the open cases are, well, what if the field K is just algebraically closed? Seems super difficult to solve. But also other things which are somehow not like number fields, but not like large fields either, things which sit a bit in between. Like you could take some algebraic extensions of the rational numbers, which is infinite, but also not large. So one example I like to give is the abelian closure of Q. We don't know if it's large. Maybe people don't think that it's large. But it's too far away from a number field for any of these proofs to work. Yeah.
Did you say C double parentheses S is a new case, newly discovered case of a large field, or a new?
Yeah,
it is a large
field,
newly.
Yes, thanks. I was a bit too fast here. So I drew this arrow from the theorem B to here. So I'm saying this is an example of a base field to which this theorem applies, and for which the result was not known prior to this theorem. It was definitely known to be a large field. So, getting a bit short on time, I want to give you a proof of this theorem. Actually, I already have. So, in a way, the reason why I gave this proof and not the Denef's original proof is because I can now kind of, by analogy, tell you how the proof of this theorem would go, at least in a very specific case. How do I do this?
You can also add more of these variables, or not? I mean,
What's that?
like you put parentheses, parentheses, S, parentheses, parentheses, and you can keep on adding more, right?
Sure. That's all. I don't want to add anything. Maybe I might. Well, memorizing this list anyway.
But and the open cases are also for concerning the theorem, not about whether they are large. The last one, whether it's large.
Yeah, great question. Right. So here this is definitely large. But the theorem we don't know about. Yeah, this conclusion. It's completely open. And this is a field. Well, if it would be large, then it's not algebraically closed, so then it would satisfy the hypotheses of the theorem. But we don't know if it's large. And I think I'm not on big number theories, but I think people think it's not large. But of course, showing that the field is not large is also very hard. Okay, so proof sketch by analogy. Sketch by analogy. So I do this, as I was saying, just for a specific rational function fields. K is large and K is not algebraically closed. I somehow want to witness that K is not algebraically closed. So let me do this in the simplest possible way. Let me assume that there is some C in K for which the square root of C does not lie in K. Actually, maybe before I continue, I should comment a little bit on the attribution here. So we did this using credit form theory, which means that the precise technical condition we need on K is that it has some quadratic extension or some even degree extension, so this can be done using quadratic forms. If you have a field K which maybe has no quadratic extension but has some degree 3 extension, then you have to do something else than using quadratic forms. But that's what I did last year. The main ideas are the same, although of course the objects become a little bit different. Okay, so I want to look at this setting and prove these 3 new propositions here. So let me just phrase what they should become. I'm not going to prove any propositions. I'm just going to phrase what they should become. If you want to do this in the analogous way. So proposition 1 prime. If K is large, then K is definitely always existentially definable in KT. Let me not say anything about how I prove this now, but come back to it. This was observed quite shortly after this notion of large was introduced by Jochen Königsmann in 2002. Here, there is also an analog, and it doesn't even use large. It's completely elementary. Let me write it actually for simplicity for some square feet polynomial, so we don't have to talk about multiplicities. Then the following are equivalent. On the one hand, to say that f can be written as g1 squared minus c times g2 squared. So remember, in the case of r, c would have been minus 1. Typical example of r, which is not a square, would be minus 1. So if you specialize c to minus 1, you get back to being a self-two squares. So there exists g1, g2. And condition 2 is saying for any valuation, let me write it like this, valuation v on f, for which the square root of c does not lie in the residue fields. Maybe give this of valuations a name, delta c. So right, this is the analog of the real places before, right? So in RT, I was only making claims. Yeah, this is now really hidden, of course, in this proposition. But I was only really making claims about x, about the behavior of x at real places. I said I cannot say anything. I don't say anything about the complex places. The analogous thing here is I only look at those places where c remains non-square locally. I need to have that f has no zero or pole. And I also need the leading coefficient of f. Leading coefficient of f is of the form d squared minus ce squared for some d and e in k. Right, so this is, convince yourself that this is equivalent to this when you're working over R, right? So it's saying everywhere in the domain you are non-negative at least. Okay, maybe I can have zeros, but not false. It's no false. Yeah, no, I mean, there's no zero. Yeah. I made it square free, so double zeros are kept. So that's yeah, so how do you prove that it's completely elementary? So induction on the degree of f. You don't use large for this. It's just a computation trick. And then what happens to this innocent proposition? Sorry about my poor water management. Yeah, so let's take some f in no infinity such that f has no zero at all these valuations. So let me write like this: v of f is non-negative at all v in delta c. Then there exists some y in k such that if I shift f by y, I get what I become of the form g1 squared minus c g2 squared. And g1 and g2 lie in. I will comment on this one, and this, so this definitely uses large. I will comment on these when you argue them if there is time. And now then the proof of theorem B. Let's see, so this should be k. And then every minus 1 should become a c, but this is confusing, so like this. C minus c minus c. Okay, that's then the proof of theorem. Actually, you might have these examples, maybe cheaper definition. Okay, I didn't really explain how this large comes in, so maybe I should say something about this. And maybe then you like this notion. How is large used? In propositions 1 and 3. So the idea is that you first prove the proposition for when K looks like, let's say, a power series field over a different field. Field of four molar series over some different field. Now, in this case, you have an implicit function theorem at your disposal. You have a topological structure at your disposal which you can use. So, if you want to prove this, you argue essentially in the same way as before. You take maybe some elliptic curve. You say, well, it has a point. Largeness guarantees that you have infinitely many points. But in fact, if you argue in this field, you can say, well, by the implicit function theorem, there is an area around the point. I mean, there is interval around your point where full of points of your curve. And maybe this doesn't give you the entire field yet, but of course, once you have some interval, think about the real numbers. Once you have a set which contains some interval, you can do some rational transformation to blow this interval up into the entire constant field. And I'm saying essentially it's the same for when you want to prove this proposition 1 prime for this field, or series field. Okay. And it's similar for proposition 3. Also there we had this argument with this curve. Essentially this was about some compactness argument, some compact topology. Yeah, you can also somehow put a topology on the space of all, yeah, you have then use non-Archimedean geometry on the space of all valuations on a function field over such a field induced by this topology, where you can also apply some compactness arguments to make it work. And then, once you have shown it for these kind of fields, use model theory nonsense to carry over. So, literally what you do is replace K by the field of four molar series over K. This is a typical thing if you want to prove things about solving equations over large fields. You first show that there is an equation over this bigger solution over this bigger field, and then bada bing bada boom, actually there's already a solution over the smaller field. In a way, this is a definition of largeness. Okay, I don't expect you to understand this. I hope you to think that, no, large fields are a weird class. I think I should conclude soon, unless there are questions so far.
Is there an example of a non-large field?
What is an example of a non-large field?
Yes, which is infinite.
Oh, sorry, I put a few here, but I forgot them. So number fields are never large.
Okay.
And then function fields. Yeah, this was really small, so that's my fault. So number fields are never large. So that is why I'm saying this theorem B doesn't cover all known examples, even though I would want it to. And also function fields themselves are never function fields of arbitrary varieties and never large.
Over any base field.
Over any base field, yeah. Thanks. That's a good question. So, okay, let me then stop writing and just talk a little bit for 1 more minute. So, this proof I gave now, as you could gather from Karim's questions, is not actually how we do it in the paper. So this I came up with a few months ago. But this is really specifically to this case where you work with a rational function field and an element which doesn't have a square root, where somehow there exists these kind of explicit, and one doesn't use quadratic forms, but this proposition 2 is or 2 prime, it's very much elementary quadratic form theory. This you don't have when you replace quadratic things by higher degree things, or when you replace rational function fields by arbitrary function fields of curves. So what we actually need is more sophisticated machinery. So we use a kind of local global principle, which was developed using field patching techniques only a few decades ago. So it's a little bit like the Hasse-Minkowski theorem, but it's a lot more involved, and there are many valuation local conditions you have to check, not just the ones you expect, but a lot more. So this is one of the things we do. Well, one has to do. Yeah, this is quite difficult actually. And then the final thing I wanted to say is, when I found these things, I was actually trying to find new examples. I mean, expand the hypotheses, but somehow I keep finding new proofs for the same theorems. So proposition 3 prime demonstrably doesn't. I mean, even though it looks kind of innocent, I was able to find using AI some example of a non-large field and some f where you really cannot find this y. You can really not find this shift. So I'm not saying it's equivalent to large, but without large, you cannot prove it. And then, of course, there's also this proposition, which is maybe a bit more innocent. But okay, thanks for your attention.
Any question?